Welcome to part 2 of two-stage op-amp design. So we are supposed to design this two-stage operational amplifier. That is, we are supposed to estimate the dimensions of all 7 transistors along with the capacitance CC in order to have desired specifications in terms of phase margin, gain, slew rate, and so many other parameters. Now these are the design specifications that will be given to design a two-stage operational amplifier. First and foremost is the gain at DC, which is AV of 0, the gain bandwidth, which is GB, and input common mode range, ICMR, the load capacitance, slew rate, output voltage swing, and the maximum power dissipation that is allowed for the given design. Now we have several steps to accomplish this particular design specifications from a two-stage CMOS amplifier. These are the design steps. In the previous video, we have seen that the compensation capacitors for establishing a phase margin of 60 degree has to be 0.22 times the load capacitance CL. So using this expression of CC is equal to 0.22 CL, we can estimate the value of CC, because for a given design the CL is given. So this 0.22 is the required condition to achieve a 60 degree phase margin to locate the second pole at 2.2 times the GB value. So using that relation we can able to estimate the value of compensation capacitor CC. So after finding out the compensation capacitance, so we need to estimate the value of I5, that is the current through the MOSFET 5, which will decide the tail current of the differential amplifier. So which can be estimated using the equation slew rate is given by I5 by CC. So in the previous evaluation we have found out CC, the slew rate is one of the specification given, so we can easily estimate what is this I5 is. So once we are through with I5, we need to find the dimensions of WL of 3 and WL of 4. The MOSFET 3 and 4 dimensions can be obtained using the VCMR max, that is the common mode range, the input common mode range, which is maximum given in one of the specification, that can be obtained using the equation. So this is what we again derived in the previous video, which is given by VCMR max is given by VDD minus under root of I5 by beta 3 minus VTH of 3 plus VTH of 1. So we know all the parameters in this equation except beta 3. So beta 3 can be estimated, where beta 3 is equal to, this is not actually mu n, this is actually mu p, because the WL of M3 and M4 are the PMOS. So this beta 3 is actually mu p Cox into WL of 3. So we'll be knowing the mu p and Cox. So once we know beta 3, can easily estimate WL of 3. So usually WL of 3 is equal to WL of 4. So these two are easily estimated from this equation. This is the parameter given. VDD is also given. I5 is estimated in the previous value, and VTH3 and VTH1 are also the given specification, so that we can easily find beta 3. Once we are through with beta 3, we can find WL of 3. Next is we are supposed to find the GM1, that is the transconductance of MOSFET 1, which can be easily estimated using the equation GB is equal to GM1 by CC. So this is to keep the zero frequency, zero should be placed at least 10 times the omega GB. Using that we can able to we know this GB is given by GM1 by CC, so we know what is gain bandwidth given. So CC is estimated here, and the unknown parameter is GM1, so I can easily estimate GM1. So next is, of course we found out what is GM1. Next is we need to find out omega WL of 1 and WL of 2. So W1, W2 are the MOSFETs M1, M2, which are a part of differential amplifier. So both dimensions are always same for a perfect matching. So we know that GM1, the earlier equation, earlier parameter which we already found, is given by under root of 2 ID1 mu n Cox into WL of 1. So here we know all the parameters except WL1. So but this ID1 is actually half of the I5. So we know I5, we know mu and Cox, we know GM1. So we can easily estimate the value of WL of 1, which is equal to WL of 2. So once we are through with the dimensions of MOSFET 1 and 2, next it is time to estimate the value of VDS5, that is the saturation voltage of the fifth transistor. So which can be estimated using the equation, that is VCMR minimum, that is common mode range input minimum voltage, which is again given by the equation which we derived in the previous video, which is given by VSS plus under root of I5 by beta 1 plus VTH 1 plus VDS5. So here we know everything except VDS5, so that you can easily estimate VDS5. So we know what is this beta 1 also, because in the previous sixth step we have actually found WL of 1. So once you are through with WL of 1, beta 1 is mu and Cox into WL of 1. So in this equation we know everything except VDS5, so that you can easily estimate VDS5. Next is we are supposed to estimate the value of the dimensions of the fifth transistor. So using the current equation ID5, so again now we can write in this form, that is mu and Cox by 2 WL of fifth transistor and VGS minus VTH whole square. So this VGS minus VTH is actually the saturation voltage. So let us write this as VDS5. So in the previous step we have found VDS5. We know all the parameters except WL of 5, so that we can easily estimate WL of 5. So once we are through with WL of I, next it is to find GM6. So GM6, we have actually derived this expression in the previous video, which says that, so we actually got this expression by equating the 0 should be located at least 10 times that of the omega GC. So using that relation, we can find out what is this GM6 should be greater than or equal to 10 times GM1. So GM6 should be 10 times GM1. GM1 we already found in the previous previous video, of course, previous step, that is in fifth step we actually found GM1. So only thing to be, how do you find GM6 is, it is 10 times GM1. Next is WL of 6. So in order to estimate WL of 6, the MOSFETs VGS, the M4 and M6 should have same gate to source voltages to have proper mirroring. So if we equate this VGS4 and VGS6, so we get the expression for WL of 6 is equal to GM6 by GM4 into WL of 4. Here we know all the parameters, then it is easy to estimate WL of 6. So we can estimate WL of 6 using this expression. Next it is to find the value of I6, so which is again related to the GM6 using the equation. GM is given by under root of 2ID mu P Cox. Now this is M6 corresponds to PMOS, that's why it is mu P Cox into WL of 6. We know everything except ID6, that is the drain current of the 6th MOSFET. We can easily find out what is I6. Then it is WL of 7. So WL of 7 can be estimated using this equation. We know all the terms except WL of 7. So we can find out what is WL of 7. Next it is just verification of these parameters, that is AV of 0, whether we are getting, because till 12th step we actually found the dimensions and different currents and capacitance value of the required two-stage Opamp. Next here it is just verify whether the DC gain is as per our designed value or not. Next this is to verify whether the output minimum is as per our requirement, and this is the power dissipation, which is given by VDD minus of minus VSS into the current, the overall current in the circuit. I5 is in the differential pair and this I6 is in the CS stage. So overall current is I5 plus I6. The potential difference is VDD minus of minus VSS. So it is actually 2.5 minus of minus 2.5, it is 5 multiplied by the summation of the two currents happens to be the power dissipation. Now this is just a summary of the design. So as you can see, this is the two-stage op-amp. This indicates, so this is the entire summary. This indicates, okay, how do we find which parameter? The first parameter is CC to be found. So that can be found using 0.22 times CL for a given phase margin of 60 degree. Next it is to find I5. So I5 can be found using the sleeve rate and the value of Cc, and W of 3 and W of 4 can be found using the ICMR maximum, and GM1 can be found using this GB is equal to GM1 by Cc. So that's what this is the equations how we estimate all these things. Next it is to find, of course, GM1 we already found. Next it is to find WL1 and WL2, that is these two dimensions. If we know GM, we know what is ID, we know what is GM, then it is easy to find WL of 1 and 2. Then to find VDS of 5, so we know what is VCMR minimum. Using that VCMR minimum, we can find what is VDS 5. And once we are through with the current through this one, so we can easily estimate the W/L, so which is using these two equations. Now you can see VDS5 can be found out using VCMR minimum, W/L5 can be found out using, since we know the current, we know all the parameters except W/L5, so we can easily find out W/L5. Next it is to find the GM6. So GM6 can be found, you can see how GM6 can be found is, so we know that GM6 should be greater than or equal to 10 times GM1. As we already found out GM1, it is just 10 times GM1. So WL of 6 can be found. Since we know what is GM6, we can easily find what is WL of 6 can be found equating the VGS4 and VGS6. So this VGS4 and VGS6 are equated to have a proper mirroring. So that's why we can able to get the relation between WL of 6 in terms of WL of 4. To estimate the value of WL6, so as we know that, okay, we are going to equate the VGS4 and VGS6, so which can be to have proper mirroring, VGS6 should be equal to VGS4. So by equating these two things, we can actually find out what is WL of 6 is equal to GM6 by GM4 into WL of 4. So by this time we have found out all the parameters except WL6. Okay, it is easy to find. Then to find I6, so once we know GM6, so it is easy to find ID6, and we can find what is WL of 7 using the equation what is given over here. Next is just to verify these parameters, AV0, Vout minimum, and power dissipation. Next, this is a typical example given. So this is the AV expected is more than 3000. The supply voltages are 2.5 and minus 2.5. The gain bandwidth given is 5 megahertz. The capacitance is load capacitance is 10 picofarad, and the slew rate expected is more than 10 volt per microsecond. The output range is plus or minus 2 volt, and VCMR, the common input common mode range is minus 2 volt to minus 1 to 2 volts. The power dissipation should be less than 2 milliwatts. So this is the circuit what we are supposed to design. You can see step 1 is we need to estimate the value of Cc. So how do we estimate the value of Cc? So we know that Cc should be greater than or equal to 2.2 divided by 10 into this is Cl, which happens to be 2.2 picofarad. So this is for a PM of 60 degree. So you are asked to choose a Cc of 3 picofarad, now which is more than 2.2 picofarad. Next step is to estimate the value of I5. The estimation of I5 will be done using the equation slew rate is equal to I5 by Cc. So we know slew rate, we know what is Cc, we can find I5, which happens to be 30 microampere. So this is I5. Next is we are supposed to estimate the WL of 3 and WL of 4 using this ICMR max equation. So here we know all the parameters. So this beta 3 is also written in terms of mu p Cox and WL of 3. So we ultimately get the expression of WL of 3 given by, this is the expression what we are getting. So upon substituting this, we can get WL of 3 happens to be 15 now. So WL of 3 is also equal to the ratio of fourth MOSFET, which happens to be 5 now. Now this is WL of, that's what we have. So this is beta 3 is mu n, this is actually mu p Cox into WL of 3. And the next is to estimate the value of GM1. So GM1 can be estimated using this expression GB GM1 by CC. We know all the parameters GB as well as CC.